Good morning. We are continuing with chapter 3. It was on kinematics in 2 and 3 directions. So we started out with vectors, and we've learned how to resolve them into components and bring them back together. And now let's see why we care. Where would we possibly use these things? Well, projectile motion is really much easier to analyze if you take the position vectors or the velocity vectors or the acceleration vectors and resolve them into components. So if you think of a projectile is anything that you throw or shoot or lob. So you hit a baseball, the baseball is a projectile. You throw a basketball, the basketball is a projectile. In my little drawing, you shoot a cannonball, the cannonball is a projectile. So we could start out and look at the big picture of projectile. If we drew it out, it's a simple parabolic curve. So it goes up, it comes down. But in physics, that's not enough information. So we break it down to the middle drawing, where it's a series of vectors. We have vector 1, vector 2. You'll notice vector 3 is horizontal. We have vector 4 and vector 5. In this drawing, vectors 1 and 5 were supposed to be equal and opposite to each other. So same tilt, same magnitude, just pointing opposite directions. Vector 1 indicates it's going up, 5 it's coming down. 2 and 4 were supposed to be equal and opposite. Same magnitude, same angle, with the exception that 2 goes up and 4 comes down. And 3 is strictly a horizontal vector. When a projectile starts out, it's going as fast as it's going to get. So as it goes up, 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 it begins to slow down. When it's at the top, it has no vertical velocity. Its vertical velocity is 0 at the top. It's all horizontal. And then it begins to fall, and the vertical velocity will slowly increase over time. So what we want to do is take each of these 5 vectors and divide them into their horizontal and vertical components. So to do that, you will notice that the first vector has a large vertical arrow, and it's the same size, just pointing in an opposite direction to the last vector. The second and the fourth vectors are similar. They have the same size vector in the vertical direction. They just point in opposite directions. And you should also notice that all 5 horizontal vectors are the same. For a projectile, in the absence of air resistance, horizontal velocity remains constant. If you have air resistance, it'll change. Or, I mean, you could have a projectile underwater, and in that case, it would definitely change. But for most of the time, in air, we will ignore air resistance. So let's look with a vector. You want to separate the vertical components from the horizontal components. That makes it easier to do the math and talk about. So what we want to do is take our equations and change them so that we can use them for projectiles. So horizontal velocity is a constant. That's a fact we need to know if we ignore air resistance. The horizontal velocity depends on the initial velocity. So how good is your throwing arm? If you can throw a baseball at 50 miles an hour, or maybe you're not so good and you're lucky to get 10 miles an hour out of it. And then the second one is the firing angle. The second one is the firing angle. And for that, for our firing angle, let me see, I left out my, so for the firing angle, what that means is, there was a little typo there, I apologize. The firing angle, that's what is the angle the object is released at. So as compared to, we usually measure that with respect to the ground. We measure it usually with respect to the ground. But you don't have to. You can measure it either way as long as you define it. So it could be with the ground, it could be with some line drawn 90 degrees to the ground. And then the last thing we know is the horizontal acceleration is equal to 0, because there is no horizontal acceleration. So our equations, if you went back to the initial definition of average velocity, it was change in position over change in time. And for a projectile, average velocity in the x direction is the same as initial velocity in the x direction, is just x direction velocity. So v bar x is the same as v0x is equal to vx is equal to delta x over delta t. So change in position over time is equal to the velocity in the x direction. And it doesn't matter if you're talking about the starting velocity, the ending velocity, or the average velocity, because we don't have an acceleration in the x direction. Your x acceleration is 0, and that's why all the velocities end up equaling delta x over delta t. So we've said our acceleration is change in velocity over time. For a projectile, the horizontal acceleration is equal to 0. So a sub x is equal to 0. If we looked at that distance equation, delta x is v0t plus a t squared over 2, and we customize it for the x direction. So we put sub x's in if they're needed. So under the initial velocity, we put a little x to go with the 0. Under acceleration, we put a sub x to remind us we're just talking about x acceleration and x initial velocity. If you look at this for a projectile, because acceleration is 0, this whole last term goes away. Because acceleration is 0, the last term goes away, and you're left with delta x is equal to v0x over t, which is the same thing as this equation. So we really only have one x equation, and that is that the velocity in the x direction is delta x over delta t. Now there are other equations in the book you could certainly use, but they're not necessary. So let's look at the vertical components. We've looked at horizontal components, and they're pretty easy because horizontal acceleration is 0. In the vertical direction, the vertical velocity changes. It depends on 3 things: initial velocity, firing angle, and gravity. Gravity is the new monkey in the mix. It's gonna make things different. So vertical acceleration is equal to the acceleration due to gravity. Vertical velocity is 0 when you're at maximum altitude. So when you are up as high as you can go, your vertical velocity is 0. And another thing that's important is that the time to get to the top of the path is the same as the time to get back to the starting point. This is oftentimes referred to as the symmetry of the projectile. Symmetry means that you've got part of it matching up with the other part of it. So for the projectile's path, if you drew a vertical line right down the middle from the top of the path to the ground and you folded things over, they would match up. So the time to get up is equal to the time to come down. But that's only true if you start and stop at the same altitude. If you are throwing rocks up and over and then they go down off a cliff, like at the Grand Canyon, which you should not do, then you get a different value. So how do our equations end up? In the y direction, if we take our equation and customize it, delta y over delta t is equal to vy plus v0y over 2. That is your same first equation. We had delta x over delta t is v plus v0 over 2, and we just popped in y's to customize it. So we have y's in place to make it in the y direction. For acceleration, the acceleration in the y direction is equal to the acceleration due to gravity, and that would be velocity in the y direction minus the initial velocity in the y direction divided by the time. So this v sub y matches up with the final time. If you wanted the total time for the projectile, if you have the total time for the projectile in the denominator, then Vy is the final velocity. If you have your delta t is the time to get to the top, then Vy is the velocity at the top. So Vy and your final time match up with each other. And then finally, we have that we take the delta x equation, and instead of x's, we put in y's. So we have delta y is equal to v0y times t plus a sub y times t squared over 2. So let's look at an example, because examples are important. We're going to throw a baseball at a 37-degree angle with an initial velocity of 20 meters per second. We want to know the maximum altitude, the total time, and the range. Range is always the x value, altitude is always the y value. So let's set up what we know and what we're trying to find and our formulas. We know that our angle is 37 degrees. They told us that in the problem. We know that V0 is 20 meters per second. They told us that in the problem. They did not give us an initial height, so we are going to assume 0. I know most people don't throw things at ground level, but because they didn't give us an initial height, we'll have to make it 0. We also know that the velocity in the y direction at the top of the path is equal to 0. I find if I don't write that down in my list of knowns, I forget that I know it, and it comes in very handy. And because they didn't tell us our initial starting position, we can assume that our starting and our ending are both 0. We also know that the acceleration in the y direction is due to gravity, and I'm going to make that negative 9.8 meters per second squared, because I'm going to say that up is in the positive direction. Up is in the positive direction. Because the ball goes up and then comes down, most people would pick up to be positive. And we know that our acceleration in the x direction is 0. What did they ask us to find? The maximum altitude. How high did it go? So y max, the total time, and the total horizontal distance. That was the range. For projectiles, you have 4 equations. You have that V0x, and remember the 0 and the x are subscripts, is equal to delta x over delta t. We know that delta y over delta t is equal to Vy plus V0y over 2. And again, the y and the 0y and those two velocities are subscripts. We know that a sub y is equal to g is equal to v sub y minus V0y over delta t. And again, these are all subscripts. The y is a subscript in both the a and the v, and the 0y is a subscript in that last v. And we also know that delta y is equal to V0y times t plus a t squared over 2 when a is in the y direction. And remember, we use parentheses for multiplication, not little dots and not little x's. And remember that just because we've written the formulas up here does not mean we don't have to write them down when we start the problem. So every time you have a problem with an angle in it, the first step is always resolve into components. Initial velocity was at 37 degrees. That's what we're going to resolve into components. So I have to draw my diagram. I'm just arbitrarily going to make the ball go up and over to the right. So this is my V0, the black arrow. We remember when we're resolving into components, we want to think of the vector as being the hypotenuse of a right triangle. So I've drawn in V0x, that's the red arrow, and I've drawn in V0y, that's the blue one. And this 37-degree angle is right down here in the left-hand corner. 37 degrees in the left-hand corner. And just like before, when you resolve into components, we're going to use sine and cosine. So sine theta is opposite over hypotenuse. In this picture, because the angle we picked was down here in the left-hand corner, opposite is V0y, and hypotenuse is V0. And now we know some things. We know that our angle is 37 degrees, and we know that V0 is 20 meters per second. And now we multiply both sides. So 20 meters per second times the sine. Why do we multiply both sides by 20 meters per second? Well, 20 meters per second is in the denominator, and the way we get it out of the denominator is to multiply both sides by it. To undo division, you multiply. That will cancel it on the right and bring it up on the left. So 20 meters per second multiplied by the sine of 37 degrees equals V0 in the y direction. So you would make sure your calculator is in degree mode. You would punch in 20 and then times sine 37 and hit equal or enter. You should get 12.037. If you don't, you need to ask me for help. So 12.037, the units are meters per second. You must write down meters per second. And you have to tell me which way does it point. And in our drawing, it went up, so we will write down up. You don't have to do the word and an arrow. I just like the redundancy. And you also need to tell me what's it equal to, so V0y. When you work an problem in physics, I will always look for three things. When you start the calculation, I want to see the formula. I want to see where you plugged in numbers into the formula, and I want to see the answer. You also want to work vertically, not across the page. Across the page just leads to trouble. All right, so we've done sine, let's do cosine. And again, you don't have to do them side by side. I just did it so I could look at the picture and get it to fit on the screen. So cosine theta is adjacent over hypotenuse. Well, the adjacent side is down here. If 37 degrees is our angle and it's the angle in the corner, the adjacent side is V0x. So cosine theta is V0x divided by V0. So cosine, the angle is 37 degrees, V0 is 20 meters per second. We plug in. The 20 meters per second is in the denominator. To get it out, we multiply both sides by 20. So 20 meters per second multiplied by the cosine of 37 degrees equals V0 in the x direction. And I got 15.973 meters per second. And it goes right because of my diagram. Not only do you have to give me the magnitude, you have to put down the units, and you have to tell me the direction. So even if you don't know anything else to do, if you have an angle in a problem, you need to resolve whatever's at that angle into components. So what do we do next? Well, normally what I would do is look at the formulas. So we know V0x, but we don't know delta x and we don't know delta t. So we can't use the first formula. The second formula is not useful. So let's look at the third one. We know G, we know V0y, and we know AVy. We know the velocity at the top of the path in the y direction. So we could find the time it takes to get to the top of the path. We could find V sub y. And so that's what I'm going to do. I'm going to find the time it takes to get to the top of the path. You will notice that when I divide things out, I also write down what it is I'm trying to calculate, because I want to be reminded of what I'm doing. It's so easy to get involved and then you write down a number and then you forget what is it. And in our equations, we might have multiple times or multiple velocities or multiple distances. All right, so annotate. A sub y is equal to g, which is equal to vy minus v0y over delta t. Remember, you have to write down the equation. If you wanted to leave off the a sub y in the first equal and just say g is equal to vy minus v0y over delta t, that would be fine. If you wanted to leave out the g in one of those equal signs and just write ay is equal to vy minus v0y over delta t, that would also be okay, as long as when you plug in, you know what you're doing. So acceleration in the y direction is negative 9.8 meters per second squared. The initial velocity in the final velocity in the y direction, vy, is 0 because we're doing it for the top of the pad. And the initial velocity in the y direction. Notice this is v0y, not v0, v0y. We just found v0y is 12.037 meters per second. You could have typed that in. I opted to round it off to 12.0. I'm going to round off 15.973 to 16. I don't encourage you round off too much. My problem was that even keeping one digit to the right of the decimal, 12.0 is still 12.0 and 15.973 is still 16. So, all righty. So 0 minus 12 meters per second over delta t. I need to get rid of the delta t. And see here, I put two steps in one calculation. I multiplied both sides by delta t to bring the delta t up on the left, and I divided both sides by negative 9.8. If that's too many steps for you to do and not screw up, make it a two-step problem. Add some more steps. And if you need help with this, I'm happy to help you. So I had to multiply both sides by delta t and divide both sides by negative 9.8. So negative 12 meters per second over negative 9.8 meters per second squared equals 1.22 seconds. A meter per second divided by a meter per second squared gives you a second. Remember, invert the units in the denominator and multiply them by the ones in the numerator. The meters will cancel and one of the seconds will cancel and it just leaves you seconds. This is the time to get to the top. It is not the total time. It is the time to the top. So now what? Well, if you've got the time to the top, you can find the maximum altitude. What I did is I went back and I looked at my formulas and said, what can we find out? We know V0 in the y direction. We know Vy at the top, but we don't know delta y. We do know delta t. We just found out the time to get to the top. So we know time to the top, delta t. We know velocity in the y direction at the top. We know v0y, and we know too. We can use this equation to find out how high do we go. We can also use the last equation to find out how high do we go. We know v0 in the y direction. We know the time it takes us to get to the top. We know the acceleration in the y direction, and we know the time it takes us to get to the top. But either one of those two equations will give you how high does the ball go, will give you y max. It doesn't matter which one you pick. I opted to use the last one. You could have used the other one. You'll get the same answer. So delta y is equal to v0y times t plus a sub y times t squared over 2. Delta y is what we're looking for. v0y is 12 meters per second. The time to get to the top, remember y is equal to a maximum at the top. If you can't remember that, you can write it down. So delta y is equal to 12 meters per second multiplied by the 1.22 seconds, that was the time to get to the top, plus acceleration in the y direction, which is negative 9.8 meters per second squared, multiplied by 1.22 seconds, that's then squared, divided by 2. Most people are better off if they don't just punch all this into the calculator as a string, but do it in parts. So take 12 and multiply it by 1.22 and write the answer down, 14.64 meters. And now let's do some arithmetic. There are a lot of different ways you could do this, but I suggest that you take the 2 and divide it into the negative 9.8, and that leaves you with a negative 4.9 meters per second squared, and then you've got 1.22 seconds that you have to square. So we still have the 14.64 meters minus. So if you take 4.9 and multiply it by 1.22 and multiply that by 1.22, you should get 7.29 meters. If you can't get 7.29 meters when you do this part of the calculation, you need to ask me for help. So 14.64 minus 7.29 gives us 7.39, I'm sorry, 7.35 meters. That's our maximum altitude. Now we can find the total time. So there are 2 ways to do this. The first method only works for problems with symmetry, where you start and stop at the same altitude. And that's because the time to get to the top is the same as the time to get back down. So total time is equal to 2 times the time to get to the top. So 2 times 1.22 seconds equals 2.44 seconds. I know I said don't work across the page. Probably it would have been better to have done it vertically, but this one instance would be okay. Mostly because it's a straight plug in and get an answer. There's no algebra involved. So the second method is used when your starting y and your ending y are different. If you throw a ball up in the air and then it goes down into the Grand Canyon, where you're standing at and where the ball ends up at are 2 different altitudes. This method would work for that. So remember that delta y is y final and y minus y initial. For us, final and initial altitudes are the same, so delta y is 0. If we are throwing things up in the air and then they're going down into the Grand Canyon, delta y will not be 0. If up is positive and you're throwing things up and then down into the Grand Canyon, delta y will be a negative number. So be careful of your minus signs and remember that it's always final minus initial. All right, so delta y is equal to v0y times t plus a sub y times t squared over 2. So we know that delta y is 0. We know that v0y is 12 meters per second, and t is what we're solving for. So a sub y is negative 9.8 meters per second squared. So we plug in, so 12 meters per second times t. And remember, I said when you have this kind of a term, go ahead and take the 2 and divide it into one of the numbers. I promise you that the algebra works out. If you have questions about this, see me individually. So negative 9, or ask the question individually and I'll give you some examples. So negative 9.8 divided by 2 is negative 4.9 meters per second squared, and then we multiply that by t squared. All right, so we've got a 0 on the left and a number minus another number on the right-hand side. What I can do is take this whole thing, this 4.9 meters per second squared times t squared, and add it to both sides. So it will disappear on the right side and pop up on the left. So I've got 4.9 meters per second squared times t squared is equal to 12 meters per second times t. Okay, I'm making progress. But what I need to do now is get rid of all the t's on one side. So I have a t squared on the left and just a t on the right. That means I want to get rid of the one that's the smallest, the t. So take both sides and divide it by t. If you divide both sides by t, the one on the right disappears, and on the left we have 4.9 meters per second squared times t squared divided by t. And it'll equal 12 meters per second on the right side. So now what? Well, t squared divided by t is just t. T squared divided by t is t. Now 4.9 times t is equal to 12 meters per second. We need to get rid of the 4.9. It is multiplied by the t, so we have to divide both sides by 4.9. So 12 meters per second divided by 4.9 meters per second squared gives you 2.44 seconds, which is the total time. And I should have written that out to the side. All right, last thing, we want to find the maximum range. Almost always, those x calculations seem to be the last ones you do, or they'll be the very first if they give you an x value. So maximum range, we know that all our vx's are equal to just vx, and it's delta x over delta t. So our velocity in the x direction, our initial velocity was 16 meters per second. That's going to equal delta x over our total time, which is 2.44 seconds. To get the 2.44 out of the denominator on the right-hand side, you multiply both sides by it, so it'll cancel on the right and shows up on the left. 16 meters per second multiplied by 2.44 seconds equals delta x. And so delta x is 39.04 meters. There are some homework problems to do. There'll be some study questions to do. You really need to practice this. I would suggest that you start out by trying to redo the example without looking at it and see how far you get. And if you can redo the example successfully, then I would move on to chapter problems or study guide problems. Okay, practice, practice, practice.